Everyone, and welcome to Chapter 7, where we're going to be learning about the equilibrium of beams. You'll understand today how to do a shear and moment diagram, and be able to find the maximum shear and moment for a given loading. Now, I'll be honest that shear moment diagrams are kind of one of those things you have to do a couple of times before they make complete sense. So if the information I give you at first doesn't seem like enough, just wait till the examples. We'll go through a few. I think it'll start making more sense then. So let's get right into it. First off, why do we care? Well, look at this beautiful deck that's being built to have this amazing view of the mountains. My goodness, I wish I had a house like that. And you see there's floor joists, and they're used to support the loads, the people and furniture and walls that might be going above them. However, those loads happen at various points. You can see this men are walking along it, and there's a bunch of supports and everything else around it. So when we're trying to figure out if this beam is going to be strong enough to hold the load, we don't necessarily know exactly what that load is going to be to start. We're going to have to search for it, find the maximum shear force, find the maximum bending moment. And then from that, we can calculate, well, will this beam actually be able to hold that? Does it need to be bigger? Does it need to be more beams? Whatever. So we're going to learn how to do that today. Okay, so there's various different types of beams, and they're typically long, straight, and they're prismatic. They support loads perpendicular to their axis, okay? Now, they're very common in almost every single structure you see, and so you have to understand how they're going to work. And as a note, the kinds of beams we're going to be focusing on in this class will be the following, because these are three determinant beams. There's also indeterminate beams. We're going to not be focusing on those. These are three determinant beams. So you can actually solve them with our equations of equilibrium. Now, the beams are usually classified by the manner in which they're supported, like it might be a pin support or a cantilever beam. It's held like this with a fixed support. All different kinds. And each of these supports will resist a different type of load. So what you can see is that that pin support can resist a force in the x and the y direction. Rolling support can only resist a force that is perpendicular to the ground that it's resting on. And finally, a fixed support resists both a force in the x and y direction and a bending moment. Now, you will not see these in real life. You will not see some beam on a roller. At least I really hope you don't. If you do, please don't go in that building. It just sounds terrifying. So real life things are much more complex. However, the performance is actually fairly similar. Like, look at these three right here. Even though all of them are technically bolted in, like right here you can see they're bolted in, and these are bolted in, and this one's just like welded in, they act very much like those we saw before. This one, even though it's bolted in, it can still flex a little bit right there. So it's not able to move in the x or y direction, but it's able to bend a little bit. This one can slide back and forth. And this one just can't move at all. So the reason we can say that these act like the supports we just saw, even though they're not like this perfectly, perfect pin support like we draw it, is because all of our deflections and twists that we're looking at least the supports, are going to be very, very small. Very, very small, and so all of this still works. It's still actually functional. Okay. Now we want to find out what the shear force and the bending moment is in these beams. So, if we're going to determine the shear force and bending moment, we have to create a free body diagram. And what we do is we cut it at a point of interest. Like, we want to find the shear force and bending moment at a certain place, so we cut it. We go, cha, and we get rid of part of the beam that ceases to exist, and we replace it with a shear force and a bending moment. We can then use our equations of equilibrium to solve for the shear force and bending moment. If you're confused about this moment, like how do I solve for that, you could take the moments around that point if you want to, and then that moment will just add into it. Now, for sign conventions, it's important to understand which direction is positive. So remember this. A positive shear force will spin the member clockwise. You see I've got the shear force right here. It's trying to spin the member clockwise. And a positive moment will bend it into a smile. Well, if I were to bend it like this, push down the middle and pull up at the edges, it would bend into a smile. I know it's silly, but it's a really good way of remembering it. Otherwise, you can just look at this little picture right here. Down on the right side, up on the left, and the moment is always trying to point onto the top of the member. Okay, so we solve our equations of equilibrium. We get the shear force and bending moment anywhere we want. And that works great. However, this right here is terrifying because if I want to use that first method, I've got to do it at every single point of interest to be able to figure out exactly what's going on. That's no fun. That's no fun whatsoever. So it's probably better if we have a faster method or a simpler method to do this. So how do we do that? Well, what we're going to do is we're going to look at a really small section of our beam. So we took that little small section earlier. You see it right here. That little section right there. I'm cutting it. And we look at that small section. Now at this small section we have a load, and that load is increasing by some factor. So over this factor of this distance, it increases to k delta x over distance delta x. So we're saying this is kind of like a triangle. We have a shear force on one side and a bending moment on one side. And then due to this applied load, there is a different shear force on the other side and a different bending moment on the other side, all because of that applied load. So how will this continuous load actually affect those internal forces? Well, if you look right here, you see that sum of the force in the y direction. When I look at that, I get one equation. I see, okay, I got my shear force right here, and I'm subtracting out my shear force. And hey, wait a second, both of those are going to cancel, which will let me see that my change in shear force is going to be equal to my applied load, so this is the distributed load, times the distance it's being applied. Okay, if we take some moments, okay, we see got quite a bit going on here. I'm doing around this point O right here. And one thing that might confuse you, say, wait a second, the moment over here though, it's not the same spot. These moments are free vectors. You can move them wherever you want, at least in these problems. And so we can act like it happens on this side if you want. And then we're going to have, of course, our shear force right here, which is going to be causing a moment. And then this applied load will also be causing a moment. Once again, you see that our moments are going to cancel. And a little bit more algebra here, we'll be able to get that our moment is going to be equal to our shear force times the change of position times a factor from our applied load. And if we take the limit of that little infinitely small part becomes infinitely smaller, then eventually we get that the derivative of our shear force is going to be equal to our applied load, and the derivative of our moment with respect to length is going to be equal to our shear force. So you see how they're connected. If you have one, you can get both of the others. Now, graphically, it'll look something like this. We'll have a applied load, and not every single problem has a distributed load. And from that, you can then see, okay, well, what's the slope of my shear force at each individual point? And similarly, I can say what's the slope of my moment, shear at each individual point, and I can find each of these. So if I know one, I can go to the rest. If I integrate them, it can also be helpful, where it looks something like this. So if I integrate over a certain section, I can find the change in my shear force over that section. And if I integrate my shear force over a certain distance, I can find the change in my moment over that particular section. So both are very, very helpful. If you have one, you get the others. Now, if you're wondering what happens if you have like just an applied force or a applied moment somewhere, it's a jump. So if it's pointing up, it's going to suddenly jump this up that much. If it's clockwise, it's going to be, can't determine how it's going to be, but I guess counterclockwise would be positive in this one. If it's counterclockwise, it's going to suddenly jump it up. If it's clockwise, it's going to jump it down. one or the other. Now we'll see this in the examples we're about to work, so don't worry too much if this is still not quite making sense for you. We will take plenty of time to go over it together. But thank you for listening. I know it went a bit long this time, but I wanted to get it all done at once. And I'll see you all soon. Have a wonderful day. Bye-bye.